Bonjour à tous et toutes. I'm doing the talk in English, but yeah, I had a wonderful year in France from 2017 to 2018. And the reason why I just got online is I'm technically now in California for the rest of the year, so it's morning. So we study climate informatics due to the threat of climate change and the extremes we've been seeing, such as these megastorms and heat waves, which can cause wildfire and drought, and their effects on communities and ecosystems. Sorry, it looks like they're mowing the lawn outside of this university in California right now. So climate informatics is based on the vision that machine learning can shed light on climate change. Now, you know, there was a Nobel Prize given out for some climate scientists recently, and also the month before that, the Intergovernmental Panel on Climate Change released its assessment report. And there certainly is a scientific consensus on climate change. But if you ask any climate scientist, there's still a lot of uncertainty and resulting open research questions where I claim machine learning can help. And let's start with those introductory pictures of extreme events. Well, there's certainly been climate change, but what is its effect going to be or has been on extreme events? Climate scientists contributing to IPCC reports put together nice summaries at the front called Summaries for Policymakers that I encourage you to look into. And as of their previous report, they summarized that in terms of surface temperature trends, we had seen a warming trend from 1901 to 2012. This is a pretty clear signal from the data about average behavior, mean behavior of a single variable, temperature. Also, in some of the educational materials that they put out, the IPCC had some very nice thought experiments, and I'll go into one of those. So if we're thinking just about the random variable temperature, maybe it has a PDF probability density function in gray, like a standard normal or Gaussian. And so the observed warming is an increase in the mean. So we know that that corresponds to shifting the mean to the right. So the x-axis is temperature, increasing as I go to my right. So of course, shifting of the mean would just move this Gaussian a little bit to the right. What does that mean? Well, the probability of hot and extreme hot weather would then increase. Now, if this is the only effect going on, then this shift tells us that the probability of extreme cold weather should decrease. But in this thought experiment put forth by the IPCC, one of the points was that yes, a lot of the changes we've observed are simply due to the general trend, the mean shift to a warmer climate. But you know, this is not all we can say about a distribution. Even thinking about second order statistics, say the variance, what kind of changes could we see if it were to change? So to continue their thought experiment, we'd start with a Gaussian for temperature, and without even perturbing the mean, just by increasing variance, of course, we get a flatter PDF in the dotted line with more spread, which is what we call having heavier tails. So that means that while we'd see an increased probability of extreme hot weather, we could also see, with higher probability, extreme cold weather. And again, you know, they're trying to pose this as an open problem to the community. And there were a lot of choices that were very idealized here, such as choices of symmetry. In fact, there's infinite possibilities going on here. And certainly among those possibilities are maybe that we've reached sort of an asymmetric distribution where we might not see any decrease in probability of cold weather while we do see increase in the probability of hot weather. So climate scientists are concerned with open problems, extremes, understanding how extremes change, or even the tails of a single variable change under climate change, is largely open. And let's think about how we, people here at this conference, machine learners, might phrase this for machine learning. Well, first off, we're studying extremes, and by definition, that means they're rare, which means that we're going to have huge class imbalance. There's not going to be a lot of positive data for the amount of negative examples, so positive labels for the amount of negative labels. And we have a time history that's rather short in terms of the measurement era. So that's not going to necessarily be enough data to learn from. And extreme events such as, heat waves involve not just temperature, but pressure, specific and relative humidity, a variety of other climatological variables. But we saw that even for a single variable, the behavior of the tails of the distribution, which is where we get the probabilities of extremes, could be changing with climate change. So it's very challenging just from historical data to do future prediction. So we don't want to have to rely on that alone. And today you've been hearing a lot of amazing different applications of machine learning. One thing that I think is very unique in this domain, this particular domain, is that there are simulations of the climate. Now, these are driven by physics, but they're highly complex. So it will take a whole laboratory 30 or 40 years to write down all the equations governing the 4 interacting systems: atmosphere, ocean, land, cryosphere. But what you end up getting at different spatial resolutions is millions of variables evolving over time, even with determinism. But then you can view the output fields, the spatiotemporal data from the simulated predictions, as input data for machine learning, and then we're back in the massive data setting, which we like for machine learning. And that's why I claim it's a good application. And let's talk again about the unique properties of data in climate. So I'll talk again about climate models shortly, but first, there are a lot of open questions around reconstructing climates of the past. So we didn't always have, measurement stations. And to understand current climate changes, it is important to understand past or paleoclimate. And instead, what we have is a collection of small heterogeneous data sets that get a very sparse view in space and time. But we have what are called proxies. So certain biological sort of proxies, such as trees or corals in the ocean, you can look at their growth rates and make inferences about temperature and available nutrients. You may have also heard of ice cores, where a big cylinder is cut out of a glacier, and the trapped air bubbles will give you a clue to the atmosphere composition at the time, and then water isotopes can be used to infer temperature. And similarly, these sediment cores are taken below lakes. Different biological species are known to thrive under different nutrient and temperature conditions. So it's very spotty. In places that we have the proxy data, it can go extremely far back in time. But as I mentioned, they are geographically sparse. So we sort of maybe have some sparse matrix completion problems there for machine learning, but definitely a small data and data fusion domain. Currently, we're in the observation era, which means we are so highly observed and sensed that we have massive amounts of data, extremely high dimensional. Now there also might be issues that we're measuring at a very high dimension, but the relevant information is in a lower dimensional manifold. So from measurement stations to buoys exploring the ocean, all the satellite products, etc. And that's called the observation era, but it only goes back on the order of a few hundred years. So it's not very long in time. So what I claim to be very unique compared to pretty much any other application of machine learning is that domain experts, so climate scientists, meteorologists, physicists, have been encoding their domain knowledge into these physics-driven climate models. And then the simulations can be done in the past. Those are called hindcasts, or as future projections, which gives us this artificial lens into the distant past where we don't have adequate data, and the distant future. So on the plus side, I already mentioned this becomes now a big data problem. Also on the plus side, this is physical knowledge. Physics gives us, some inertia, conservation laws, and therefore predictability. And the modeling assumptions encode scientific domain knowledge and first principles in the physical sciences. That said, on the negative side, these are run as computer simulations, and they're never simulated exactly at scale. So you may have a grid box that's on the order of tens or even 100 kilometers per side. And it's known that you can't accurately model a cloud or a variety of other moist processes at that scale. So there are discretization and what climate scientists call parameterizations and other approximations to deal with those scale issues. Moreover, it is, computationally hard to do things like couple between the atmosphere and the ocean. Think about difference in time scale. The ocean circulates on the order of hundreds of years. The atmosphere circulates on the order of weeks. And also spatial scale. As I mentioned, clouds have to be resolved at a very fine spatial scale. Clouds hold the key to really unlocking how different interventions are going to affect climate change, but they cannot be resolved at the scale of these global models. And then the other caveat is both hindcasts into the way distant past and any future predictions cannot be validated. We can only validate essentially during this observation era where we see what happened up until the present day. Okay, so that's the sort of data scope of this domain. And I want to mention that there is already a critical mass sort of communities researching at this interface. I've been involved with climate informatics. Okay, I'm getting an Excel message. I really hope it doesn't shut down my presentation. Oh no, that was just for Microsoft Excel. So climate informatics is now in its 11th year. We launched it in New York at the New York Academy of Sciences. Then we went to Boulder, where the National Center for Atmospheric Research is in Colorado. And we've always had strong participation internationally, especially France. Actually, we were at ENS for the 2019 conference. And then the 2020 conference was supposed to be Oxford, but it was online. And this year we're switching up from fall to spring. So in fall, we did the hackathon, and tutorials were online. But our next conference will be in spring at a NOAA Center for Climate Data in a beautiful mountainous part of Asheville, North Carolina. You should all come and meet climate scientists. We usually have travel funding for student-submitted papers. And currently, I'll mention I'm at a 7-week-long program in California specifically on machine learning for the study of climate. This one is more geared towards climate science rather than all broader aspects of climate change. So I encourage you to get involved. Just the Paris region itself has a lot of people in the climate change and climate science domain, and the best way to do interdisciplinary research, I think, is to find someone and directly start building that research relationship. It could be a fellow student. And And then I also want to mention in the broader realm of environmental data science, we now have a journal dedicated to promoting work on AI, machine learning, and other fields of data science, specifically on climate change and other environmental issues. And I would also encourage you to submit to that. In the early days of climate informatics, we, myself and Arindam Banerjee, were speaking at NeurIPS, a top machine learning meeting, and trying to get people on board, trying to interest grad students in working in this area. And we did our best at listing down some major areas of problems. The list is not complete, there are more problems, but I'll just give you a taste. So I did spend some time talking about paleoclimate. Before we had measurements, how do we reconstruct climate? And those are those sort of sparse completion questions from those proxy measurements, such as tree rings. In green are things that my lab has worked on, and today I'm only going to talk about one or two of those. I'm going to talk a lot more about climate downscaling, going from a coarse resolution model forecast down to what's happening in my very postal code, which more and more, local governments are asking for. A long line of work in my lab that I'm not going to be talking about today is about taking forecasts from ensembles from different countries who their forecasts actually quite disagree as we go into the future. How can we make an ensemble prediction that's robust using algorithms we had developed for online learning with non-stationarity in both space and time? More broadly, this data is all spatiotemporal with really interesting long-term dependencies. So it's a really rich playground for any spatiotemporal learning methods. And more broadly, back to the introduction, there is an open problem around extreme events. I'll touch on that a little bit today, but that's a direction my group has started to work on. That said, if you go to Jussieu or Saclay, there's plenty of labs working on climate. There's something called SAMA IA et Climat, which is an email list. There's also something I think called AI for C. So just in the Paris region alone, you can definitely find collaborators. And then in terms of ML approaches, I'm going to mention a couple today, but a lot of different domains of ML can play a role here. And in particular, I'm going to focus today on unsupervised deep learning, which is also interesting from a methods perspective. I just joined at the end of the last talk because it's the first thing in the morning over here, but I did hear him give a quick reference to VAEs. I'll talk a bit more about those. So mostly unsupervised learning. Sometimes it's in a semi-supervised pipeline, and then I'll also explain why sort of semi-supervision can be a way to understand why some of these work. And I'll do so in two case studies coming from the domain, avalanche detection and downscaling, going from coarse to more fine resolution, which can be applied to anything, but we did examples for temperature and precipitation. Okay. I'm not sure how questions are being run, but I'll try to, this would be an okay stopping place for just a few intro questions, and then I'll present two case studies and try to take questions after each of those. But I welcome that. I generally sort of like to front load my presentation. So I'm going to jump into a slide that looks a little bit technical, and this is just meant to map in somebody's mind who's familiar with deep learning from supervised to unsupervised. That said, people come to these conferences with all different levels of background, and I will be getting things working things forward from the case studies. So this is just maybe something that you can skip if you're not sure what I'm talking about. But if you are familiar with deep learning in a supervised setting, no matter what your architecture is, let's abstract that away, and it's governed by some parameters W, you know, the parameters, the weights at all the weights and offsets at all the layers. And so the action of the network on an input, say an image, a vector, whatever the form your input is in, so an individual input example X is, we'll just call F sub W. So I've abstracted away the entire architecture. And then we'll just denote the output of the network as Y hat. Again, it could be a field, a tensor, a vector, a scalar. It depends on your problem. But supervised learning will make a prediction loss function that compares the output of the network Y hat on your input X to the desired output, what that we call the label. That's the ground truth label Y that you know should be associated with an input data, a particular input data point X. And so then loss functions can be designed that compare the network's output to the target output. And then how are these estimated from data? Well, given many, many example label pairs, XY pairs, we can, you know, run them through the network, either, you know, in mini batches, or usually we're not doing full gradient descent where we take the gradient of the loss on the entire data. We might do a stochastic gradient descent, but essentially what we're doing is we're looking for you know, the downward direction in the gradient of our prediction loss in order to try to minimize it, and taking steps minimizing our prediction loss, and then pushing through the incremental updates of weights at different layers via just the chain rule from taking derivatives is how we estimate in an iterative fashion all the parameters of the network. Okay, so if you're okay with that abstraction, then I would just invite you to consider what happens if I don't have a label Y, as this is the case in many, many domains. You don't have data that's conveniently annotated. I also heard among all the French that was being said in the previous talk, occasionally the word active learning in English. And, you know, certainly there are semi-supervised options or active learning options where you have access to some labels. But if you have absolutely no labels, you should still be able to do deep learning as follows. So you still have whatever your network choices are and the entire network operating on a data point indicated as F sub W, where W is the weights to be fitted and learned from data. The only difference is that there's no label Y, so my loss cannot be a function of any other external thing, so I might as well make it a function of the input to the network in addition to the output of the network, which I'm now denoting as X hat. Okay, so especially as we consider either the entire training data set or also on mini batches, we can think of losses or objective functions, say, for clustering. Many clustering objective functions, you know, only depend on the data set by definition. And that's a side note that I wanted to mention, since I'm going to mostly be talking about embedding and specifically dimensionality reduction at first, although later I'll talk about downscaling, which actually increases the representation dimension. So the trick is now just write down some function that you want to minimize, and it can't depend on an external value, so you can just have it depend on the network's input and output, but still we'll do gradient descent and we'll use the chain rule to propagate each step that we need to take in our parameter space W to accomplish some approximate form of gradient descent. Okay. So for those of you that was helpful, great. For those of you that took a break to check email and wait for the case studies, we're going to go to the case studies now, which are a semi-supervised pipeline that leans heavily on unsupervised learning for avalanche detection, and then an unsupervised technique that we use for downscaling. So the entire pipeline is semi-supervised, but we're going to rely heavily on unsupervised learning, and this is part of a thread of our work on machine learning for extreme events. While in France, I had a wonderful postdoc, Sophie Giffard-Roissin, who led our work on hurricane track prediction, and is now in Grenoble at IRD. Another work I wanted to point out was this pretty creative idea, actually using topic modeling from text mining, but without, actual text data, with climate data, to learn climate topics, which could be everything's in a normal state or extreme wet state, extreme dry state, etc., which allows your definition of an extreme to be completely soft and probabilistic and multivariate and detect multiple types of extremes, all of which were new in the domain literature. I forgot to put, so the 2019 version, the version that appeared in Paris of this, was just a supervised approach with a CNN that we do compare to as a baseline. But this was from the 2020 conference, same authors. It's about avalanche detection, and it's with my current PhD student, Somia, and my former postdoc, Sophie, who I mentioned, in collaboration with a whole bunch of people at Météo France in Grenoble. Okay. And, there seems to be some correlation with the danger of avalanche with climate change. I won't say anything about causation, but at the minimum, I can say that studying extremes such as avalanches is needed when we want to look at climate change impact. And now back with my machine learning hat on, why is this interesting? So I've got a problem where I'm trying to detect rare events. So it's severe class imbalance, as I mentioned at the outset. And also in this particular problem, I only have a limited amount of labeled data. So I do have some ground truth labeled data, but I have a fixed amount, and it was actually measured on the ground. Météo France sent out a survey of trekkers to certain avalanche corridors in the French Alps to inspect the ground. So you just have snow, but you're trying to tell, did the snow have an avalanche deposit on it or not? And so in this case, we really only have two kinds of data. We have the labeled data, ground truth measured on the ground. And then we have as much, satellite unlabeled imagery as we want. So in this case, we're using synthetic aperture radiation imagery. What you might ask, and what we didn't have access to, was some in-between product. Maybe the SAR imagery with segmentations drawn by human experts. We don't have that. Our Météo France colleagues said it was hard even for human experts to do that, although they were trying to train them. But at the time, we just had as much unlabeled satellite data as you want, and then some fixed amount of labeling in certain avalanche corridors, couloirs. Okay, so to build intuition about our approach, first let me give a basic approach and then explain how we propose to change that. So, we're just trying to detect, this is not a prediction task. Avalanche prediction is also extremely important, but at the time they were asking us for avalanche detection from satellite imagery. So it's essentially an anomaly, a rare event. So we can do some sort of pipeline that will give us anomaly detection. And the previous talk mentioned VAE at the end. I'm going to mention it quickly now, and then I'll actually explain what it is. But it's an unsupervised deep model that we can learn on the image data. And it would make sense that if you modeled the negative examples, image patches without avalanche in them, then we could then use it for anomaly detection as follows, right? We could have a threshold on the reconstruction error above which we classify an unknown image as avalanche. So once the VAE is trained on images without avalanche, then when we want to use it to classify, we send the image with unknown label through the VAE and then compute the reconstruction error, which is how well the output of the network matches the input. And if the network was not trained on these negative examples, then we expect the reconstruction error to be high. And so we could, by tuning the threshold as a hyperparameter via using some label data, we could use this as an anomaly detector classification. So this is pretty intuitive, but where is supervision coming in? So certainly 3, to tune the threshold above which I would classify as an anomaly or an avalanche, I certainly need labeled image patches. So I need to look at the ground truth survey, compare it to the locations of the images, and get some image patches labeled as no avalanche and some as yes, so that then I will choose the threshold that tries to minimize my error on classifying between the no and the yes. But with this simple idea, actually supervision is needed sort of in a bottleneck here between 1 and 2, because I'm training only on negative examples. That means I have to waste some of my labeled data even just to check different image patches and send the negative ones to the VAE. So our insight was actually for step 2, let's skip this step 1.5, no labeling, no supervised bottleneck before step 2, which means that all we can do is just train the autoencoder on all satellite imagery, not knowing whether it's negative or positive. We'll hold some out and use labeled data to label it, and then that'll be the validation set, but we'll use that labeled data only to tune this hyperparameter. Okay, so what's an autoencoder? So an autoencoder is actually a great example of a pretext task, which is one way that people have been using to explain or design unsupervised deep learning algorithms these days, because it's sort of a stupid task. We learn these parameters in these 2 boxes to get a machine that, given an input, basically does a noisy version of identity function. We were minimizing a loss that's trying to push the output as close as possible to the input of the network, but that's not a very useful machine in terms of giving us an identity function that's not even very good. But it's a pretext for learning a compact representation. So we send the data through a lower dimensional bottleneck and hope that if we train on many images, then the weights that we've learned at this bottleneck will somehow be representative of the distribution. And so that's what we call a dense autoencoder, where we go from a higher dimensional to a lower dimension before getting the higher dimensional output. Wide autoencoders, where we actually project to a higher dimension, pop up in things like cognitive science. It's conjectured that the human visual system is making a higher dimensional embedding of what we sense in order to then have sparse representations that keep the code for different signals well separated in that space. Okay, but in climate and in many data domains, you'll probably be wanting to do dimensionality reduction with these. And then moving to a probabilistic or generative framework, it would be nice to actually learn a distribution over this lower dimensional space. And VAEs were originally introduced where you would learn some Gaussian. So you would start with some prior set of parameters, but after training on many data from the distribution, that you would have a Gaussian that fits better to a lower dimensional representation of your distribution. Okay, and hopefully I'll have time to get to the second project where we move away from this Gaussian assumption in a different application using a technology called normalizing flows. So to understand the straw man version, or the first version that I mentioned, this part here is the autoencoder, and it would be learned only on negative examples, which means there's this step where we look at the ground truth survey, we look at the images, and only take those that don't have avalanche deposits in them according to the ground truth survey. So that's supervision, but then we train our autoencoder. Alternatively, what we could do, and this is what we suggest, is just take image patches without having used up any of our labels. So we don't know if there could actually be avalanche in these images, but still learn a VAE. And then in either setting, to implement the anomaly detection pipeline, there is this supervised decision we have to make. We're going to make it using this threshold on the reconstruction error. And I have it in green because it's a hyperparameter that we're going to tune. So how does that work? We have to take labeled images using the ground truth survey. And now the autoencoder has been trained. And so if we send an image through it, there's going to be some reconstruction, and we want to set the threshold such that images labeled as avalanche have a reconstruction error greater than the threshold, and images labeled non-avalanche have a reconstruction error lower than the threshold. This is just hyperparameter tuning on a labeled validation set. And how do we use this? Well, once the threshold has been tuned, then we can use this in a supervised classification way, right? We can send in an unlabeled image, get an image reconstruction, compute the reconstruction error compared to the input, compare it to the threshold to tell us whether we would say it's avalanche or no avalanche. Okay, I'm speeding up a little bit. I think actually I may have started late, but my clock says that I've gone 37 minutes out of a potential 40 minutes. So if the moderators want to let me know, but let me at least finish with the results on this project, and we'll figure out if there's time to talk about the variational, the normalizing flow project. So with this project, Météo France at the time had been designing non-machine learning techniques to look at this satellite product, this SAR imagery, and design some kind of deterministic threshold to locate avalanches, but they weren't really happy with the results because you'd get like a little spot right in the middle of a ski town. And these were sort of some unlikely side effects and results of just thresholding values. I think maybe because it was pixel wise and didn't really look at neighbors also, and it was not learned. Okay. In general, you're not going to see much good accuracy from any of the techniques. So their baseline technique got accuracy of 0.58. And they said it was hard to even, at the time, they didn't even have humans that had any skill at it. We went ahead and tried CNN in a previous year, and that did not even outperform because we had to create an artificially balanced training set, which meant we had much less data, and we're already starting from supervised data, so we could only use image patches corresponding to where the ground truth survey had taken place. What I talked about today were both semi-supervised pipelines, but in one of them, there were labels required even before learning the VAE to sort out just negative examples to train the VAE on. And on the other one, we just leaned heavily on unsupervised learning and just trained the VAE without checking any labels beforehand. And so there's a significant lift by doing the latter. So this might seem strange at first because, of course, the unsupervised one was trained on data that might have avalanches in it. But here, like the main important things to remember. Just like in any study, if you pick up any machine learning paper or computer vision paper in a top conference, any study comparing different methods in a table like this has to make sure that all the algorithms are treated fairly. Meaning, if they have hyperparameters, each algorithm independently tunes their hyperparameter to optimize, do the best job at minimizing your prediction error or your accuracy on a labeled validation set that is disjoint from the training set. So between training on only negative examples or on a whole bunch of labeled data except for the validation set, both methods that we proposed would still get to have their threshold tuned for the supervised wrapper that implements anomaly detection outside of the unsupervised learning. And the values of those thresholds most likely are going to be quite different. But the unsupervised one has been trained on more data, which generally means less overfitting, better generalization. And the additional data that it's been trained on might have avalanches in it and is therefore quite noisy then in the feature space. And somewhat unintuitively, if you're not familiar with machine learning, training in sort of a noisy or more explorative view of the feature space is a form of regularization that will help you generalize better. So anyway, this fully unsupervised method holds up also in terms of ROC curves as doing the best. And then sort of my outlook here is that I showed this as a case study in Avalanche, but in general, we are left with an outlook that if you have, especially when you're in a rare event setting, and especially when your data is limited, to lean as heavily as possible on the unsupervised part of the pipeline. And we really, in this example, showed that you can use your labeled data only for hyperparameter tuning. So only for that labeled validation set that's needed when your entire pipeline has a supervised component, meaning your entire pipeline is semi-supervised. More generally, this is an example of a virtual sensor. So the sensor being used was humans going into the field, and that was dangerous for them. And so if we can map now from satellite data to what the humans would have said, that frees up the need for sending humans into the dangerous environment. But more generally, like in the US, our NOAA, which is like your Météo France, is interested in virtual sensors where you could take some satellite product and use it to infer what radar would be saying in a specific location. Radar is expensive and we don't have it in all locations. So can we use machine learning to model mappings from some satellite products that we can get cheaply to radar. And then of course, as I mentioned, a next step for the avalanche problem would be forecasting. So I know you probably guys want to get to your aperitif. I do have another topic. Let me defer for a second, to take any questions, and also for the organizers to tell me whether to proceed forward with the topic. Be very careful anytime you do interdisciplinary work about language, because words have different meanings, even in a single language, say, even within French or within English in different fields. Downscaling in climate is going from a coarse grid data to fine grid, which might be called actually super resolution or upsampling of sorts in computer vision or machine learning. So down is up. We did a domain alignment approach using a method that uses normalizing flows to do generative downscaling, meaning you can get a whole distribution of images at the coarse or fine scale. And it's actually, you could go in either direction. And I guess the only other thing I wanted to maybe mention is normalizing flows. So if you were unhappy that a VAE was ultimately only able to learn a Gaussian over your feature space, some great work is coming out, including in France, on normalizing flows, where you might start with a simple prior like a Gaussian, but you learn a series of invertible transformations to get a much more complicated distribution over your latent space. So much more complicated posterior over your latent space. But still balancing off against some regularization that penalizes your distance from the prior to trade off against overfitting. Anyway, it works quite well. And it allows you to have sort of a generative model now. And there's interpretability, like you can start with input images, then walk through the latent space and generate images at fine and coarse scales. And yeah, there's a variety of other open problems. These days, I'm particularly interested in what is a good pretext task to learn spatiotemporal features. And also, people are doing this now for video and movies, like in industry. But since I care about climate, we don't have cats or actual objects. We have patterns on fluids, such as storms, atmospheric rivers. Everything's very ephemeral. There's a lot of interesting open problems there. But anyway, I thank you for your time. I'll let you get to the apéritif, and happy to discuss if people want to stick around for questions.
Well, thank you, Claire, for this presentation. And so do we have questions in the room? Yes.
Yeah, I have a question. Thanks, Claire, for the nice talk. So maybe I missed something. I'm still trying to understand the unsupervised VAE approach for avalanche detection. And is it correct that what the unsupervised VAE does is to provide a score for outliers, and then you optimize the threshold? But I'm just surprised that outliers is synonymous to avalanche here. So did you check, for let's say the errors you do, maybe you detect true outliers, which are just not avalanche in the errors?
Right.
Did you check that?
Yeah, we have gotten, so in this example, we were able to just simply characterize them as avalanche. Yeah, from human inspection, that was okay. Because we just had images of snow with differences in texture, whether there was an avalanche or not. Some people have said, oh, what if there was a polar bear, or, okay, not a polar bear, but whatever you get in the Alps. And that's a good point, but this whole thing could be refined. You could maybe have a whole set of different thresholds, and then different intervals correspond to different classes of interest. That would be one way to expand to a data set that's maybe not as simple and boring as ours. Nice question.
So when you ask questions, maybe just present yourself, because Claire cannot see us.
Hi, Claire. Thanks for the talk. It's Liva. Voilà, we exchanged mails, so thanks a lot for being there. I have a question that is directly related to the news and the thing that happened last week and the week before. Is there I don't know, I don't even know how you say that in English, but the COP26? Is it the right name in English? Let's say it's
yes.
COP26.
Yeah.
Okay. All right. So was there like a slot or something telling that informatics and climate is now a topic that is looked at by politicians and states and governments, or what is the place of the things that you do in the overall understanding on how to take care of the planet and the climate?
Yeah, the global economic and policy community is becoming aware. So in 2018, the World Economic Forum put out a report called AI for Earth, calling on the use of AI research in a variety of areas, including climate informatics. They cited us. And in the last two COPs, an organization called Climate Change AI has been hosting some events. And then there's also something called GPAI, which is an organization among OECD countries, which is about responsible use of AI and governance. But within that, I'm on a committee on climate change and biodiversity. And this committee commissioned a report, again, on AI for climate change that was released around the time of COP and I believe presented locally there. So some governments are more on board than others. I mean, France is on board. There has been, you know, a lot of AI funding increases at the highest levels in France, and also an acknowledgement. So there was a funding program a few years back called Make Our Planet Great Again in France, which would give jobs to climate scientists moving to France from other countries. So it really depends, of course, country by country. And we also understand AI is, so in my view, it's the cheapest way to unlock insights out of all the data that we're both collecting and simulating. These simulations have now become so complex and created so much data. A few years back, a climate scientist told me that more data has been generated and stored as the output of the physics-driven models than all satellite data retrievals. But it's being created, and then it then needs to be analyzed to get findings that will be helpful for decision makers. So to some extent, yes, governments are understanding that AI can help in the fight against climate change. That said, AI research isn't the only thing that needs to get funded to address climate change. You know, I'm really concerned around environmental justice. So any interventions or preventions should take into account that some communities, at least in the US, have borne the brunt of the most pollution or the least greening in their cities, or clean water or least services, worst air quality, leading to disease, and helping vulnerable populations should be front and center. There's also issues that, you know, the US and first world countries are polluting the planet, and then people in the global south in hotter climates are bearing the brunt. So there are a lot of social and political issues. Not all of them can only be solved by AI alone.
All right, thanks a lot.
Okay, perhaps a last question. So maybe, Claire, to conclude on all of this, a question which is related would be, what would be your advice to impact collective policy decision making with the research of on AI?
So I really stayed out of politics for a while, because at least the way the incentive structures work in universities in the US is that, you know, you really need to focus on the science at first. I think a great message, not sure how you're going to give that message, is that, you know, it's very easy for the public now to believe in AI. In fact, they believe in AI too much. They think it's magic, right? Because they see ads pop up from things that they emailed about or did a web search. So everybody knows AI, machine learning works. And to view this as a completely data-driven way without any politics or deniers, just to make some conclusions for climate change related decisions. So we know AI works, and AI can help shed light on the uncertainty that there is. That might change the mind of some climate deniers, but probably not others. And then just maybe as parents to children, encouraging good science education. France doesn't have a problem there. France has some of the best science and math education that I've ever, been exposed to. But in the US, I think problems around not understanding science or not understanding climate change definitely stem from problems in our educational system, where I think policy change is urgently needed.
Okay, thank you, Claire. Thanks a lot for your time and your
Thanks.
presentation.
Have a good evening. Thanks for the invitation. I guess I'll log out now and let you do the rest of.
Okay, let us thank Claire again.